Hi, my name is Luke Laver, and today I will be presenting Lab 4 for AE 2610, which is combustion dynamics in a Rijke tube. The purpose of this experiment is to become familiar with pulse combustion and its quantitative and qualitative characteristics. The device in question is a Rijke tube, a simple device that produces acoustic oscillations under certain conditions. The Rijke tube was invented by Pieter Rijke, a Dutch physicist, in 1859. The device is simply a vertical, open-ended tube with a heat source located in the lower half. Inside the tube, acoustic pressure waves are driven by the heat source, which drive velocity waves. These waves in turn drive heat oscillation, forming a feedback loop. This same concept is applicable to pulse jets, which rely on a similar system, but are closed on one end. Additionally, chemiluminescence will be used to estimate the combustion rate, as combustion is a chemical reaction that emits light. This experiment was performed in a controlled Georgia Tech lab environment pictured on the left. 3 pressure transducers are located in the tube at 1/4, halfway, and 3/4 of the way up the 72-inch tube. Additionally, a photomultiplier is looking into a window in the tube to quantify the reaction rate. The air is exhausted upwards and a fan is pointed up the tube due to the long exhaust tract. The flame is moved up and down using the scissor jack shown as the various experiments require. The instrumentation used for this experiment are 3 piezoelectric transducers and a photomultiplier. Piezoelectric transducers output different voltages depending on the distortion of a small membrane inside them, allowing them to measure pressure changes accurately. Meanwhile, the photomultiplier measures the photons ejected by the reaction. Specifically, this experiment looks for photons due to OH chemiluminescence, for which an appropriate filter has been placed on the PMT. These devices are hooked up to power supplies and amplifiers, but ultimately the data acquisition system, which allows data collection via the computer. Additionally, there is a thermocouple and a flow meter, but their measurements are not used in this analysis. This experiment was performed 4 times, first with the burner at the same height as the middle pressure transducer with the pressure valve release open. Then the valve was closed and the experiment was performed again. Then the same experiment was performed at burner positions 2 inches and 6 inches higher than the initial position. Finally, once the burner was raised high enough for resonance to stop, the burner was lowered again to find the height needed to restart the oscillations. Values from the transducers and photomultiplier were measured 5,000 times in 1 second in each case. In the video about to play, the flame oscillations are clearly visible and the oscillations are audible. Near the end of the video, the flame reaches the 6-inch position and oscillations cease. And there you hear them stop. The table shown provides reduced results for all 4 runs. Here, the relative strength of each signal is represented along with the peak frequency and phase angle relative to the middle pressure transducer. Notice that the pressure magnitude is much larger for the 2 cases in which resonance occurred, the 0-inch and 2-inch height runs with the valve closed. The pressure values represent the sound pressure level in decibels, which represents the strength of the pressure waves relative to the human threshold for hearing, which is a known fixed value. Note that in the cases where resonance occurs, the waves oscillate at 97 Hz for all 3 transducer locations, which is very close to the predicted value of 94.61 Hz, which was obtained by first calculating the speed of sound, then dividing that by twice the length of the tube. The frequency represents the natural frequency of this particular tube in these testing conditions. The first thing to point out is that even though resonance only occurred for runs 2 and 3, the resonant frequency matched for both cases despite the difference in burner height. This proves that the burner location does not affect the resonant frequency of the tube, so long as it permits resonance. Next, the values shown here indicate that all 3 pressure transducers were more or less in phase for both cases in which resonance occurred, which makes sense as these measurements represent different points of the same pressure wave. It's also important to note that the photomultiplier data is only reliable for the case when the burner is at the 0-inch location. Any higher and the flame is out of view of the photomultiplier. This becomes clear when comparing the RMS voltage for each case. However, when the flame is visible, its resonant frequency matches that of the pressure waves. Additionally, the heat source fluctuations are roughly 90 degrees out of phase from the pressure fluctuations due to the nature of the feedback loop present in the system. Lastly, after resonance stopped, the burner was lowered until resonance started again. It needed to be as low as -0.6 inches to start resonating again, indicating that resonance needs near ambient pressure to start, but is maintained so long as the flame remains in the lower third of the tube. A filter made to block 415 to 450 nanometers of light would not work for this experiment, as the light that is important for this experiment is that ejected by OH chemiluminescence, which occurs in the range of 306 to 311 nanometers. Next, if we wanted to create a tunable Rijke tube, the most effective approach would be to change the length of the tube. This could be accomplished with some extensible mechanism that doesn't greatly affect the surface smoothness inside the tube. Another, likely more costly option is to change the atmospheric conditions around the tube, as the natural frequency is sensitive to temperature, ambient pressure, and density. All in all, the Rijke tube is a simple device that has major applications in aerospace in the field of pulse combustion. Interestingly, turning the tube sideways or upside down breaks the feedback loop, as the velocity and pressure waves are out of phase and cannot drive each other. Also, pulse combustion is useful in aerospace because nearly all the heat generated is exhausted, and the velocity oscillations tend to strip away the boundary layer inside the combustion chamber, increasing its effective volume and minimizing losses. Additionally, the pressure oscillations result in excellent fuel-air mixing, and the process as a whole is just simple, minimizing risk. Thank you for listening.